The moment of inertia, which we denote with I, is kind of like the mass equivalent for rotation. Just like how linear velocity has angular velocity, we have torque for linear force. For mass, we have the moment of inertia. Now, before we get into that, we also discussed in the last video that angular acceleration is proportional, which is this symbol, to the net torque. So the sum of all of the torques. This corresponds with Newton's second law, which says that acceleration is proportional to the net force. I'm going to go and derive a very important equation, which we'll be using today. It's optional. If you don't care and you're only here to solve problems, you can skip it. But I highly recommend at least watching it because it tells you that the formula doesn't come out of thin air. So let's examine a circle with the center as C, radius R, and an object of mass m traveling around the circle. We can relate torque to the moment of inertia and angular acceleration. And here's how we're going to do it. Let's apply the second law. So take a look at Newton's second law, F equals ma. Tangential acceleration is radius multiplied by angular acceleration. So we can plug this in here. And here's what we get. F is equal to m r angular acceleration. Torque is rf, which is equal to r times this value for f. When you expand, you find m r squared times angular acceleration for torque. And the moment of inertia is given by mass times radius squared. Guess what? We can substitute this in here. So now torque is equal to moment of inertia multiplied by angular acceleration. There we go. That means torque is proportional to the moment of inertia. Anyway, we've dealt with one particle rotating in a circle, but anything real, any solid object is a collection of millions of little particles all at different distances from the center. Every tiny bit of mass has its own tiny torque value, and that depends on the distance. How do we handle this? For each particle, torque is equal to Rf. Let's label it with I. And each particle also has its own mass. Now, let's apply Newton's second law for all of these particles. And remember, tangential acceleration, as we found earlier, is radius times angular acceleration. The torque of these objects is radius times this force. So we could plug in the value for this force to get radius times mass radius angular acceleration. And that's equal to m r squared angular acceleration. Now we have to add up all of these millions of little particles, which is this. The sum of all of these mini torques is equal to the moment of inertia multiplied by angular acceleration. This here, we've done it. This is Newton's second law in rotation form. But what this means is that every tiny piece of mass resists rotation depending on its distance from the center. And when you add it all up, that is the moment of inertia. The angular acceleration that torque causes is scaled by this inertia. Just like how when you apply a force to cause acceleration, it's scaled by the mass of the object. When the mass is further from the axis, it's harder to spin. And when it's closer to the axis, it's easier to spin. You need less torque. That's why when you have an ice skater, when their arms are out wide, there's greater rotational inertia. It's further from the axis, so they spin slower. But if you ever notice these ice skaters, when they pull their arms in together, close, they, in real time, immediately speed up. But they have the same mass. The thing is, it's distributed differently. It's closer to the center now. There's less rotational inertia. Imagine you have a long metal rod. And this metal rod, it's very, very light, so we're going to ignore the mass. You have one object on one side weighing 3 kilos and one object on the other side weighing 6 kilos. The rod is 5 meters long and the axis of rotation is right in the middle. Let's find two things. The first thing is the moment of inertia when the axis is right in the middle. The second thing we'll try and find is the moment of inertia when the axis is 1 meter to the left of the 3 kilo mass, so right here. Okay, let's go through this step by step together. So in problem A, the axis is right in the middle, like our diagram shows. Each mass would be 2.5 meters away from the axis, right? Because it's 5 meters long in total. The moment of inertia formula, which is on the free cheat sheet in the description, is this. All of the masses and all of the radius squared added up. The mass radius for the first object is 3 kilos times 2.5 squared. Don't forget the exponent. Plus the second mass radius value being 6 kilos times 2.5 radius squared. This gives us 56.25 kilograms times mass squared. It's a weird unit of measurement, but I want you to remember this number, 56.25. That's the moment of inertia when the axis is right in the middle, so they're evenly distributed. What about if the axis of rotation was moved to the left? So imagine this is the same metal rod. We've got a 6 kilo object and our 3 kilo object, and 1 meter to the left of the 3 kilo object, we have the new axis of rotation. So now the distance is something like this, with the total distance being 6 meters. What's the new moment of inertia? Well, let's plug in our values. We have 3 kilos times 1 meter squared plus 6 kilos times 6 meters squared, since that's how far it is now from the center. The moment of inertia is now 219. And this is a big jump. Why does this matter? Moving the axis changed the distances dramatically. And because the moment of inertia is dependent on radius squared, a small change in distance is a huge change in rotational inertia. And here's something interesting. The mass that's further away matters the most for inertia. Look at this. Look at the inertia. For the first object, it's only 3. But for the second object, the dominant object, because it's the most furthest away, it's 216. That is a big difference, and that's because it's the one furthest away. So the location of the mass matters much more than the size of the mass. Now let me show you something. I stole this from Google. Depending on your shape, the moment of inertia is not always simply mass radius squared. For example, here is 2 over 5, 1 over 2, 2 over 3. It depends on if it's hollow and what the shape is. Now, I wouldn't worry about this too much. It is kind of important, but I think knowing the concept matters more. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up.